In this video, I introduce backpropagation through time for recurrent neural network. The backpropagation through time finds the relationship between the loss error and the model parameters W and B. The goal is to minimize the loss error by changing the model parameters W and B. Here, suppose we have one RN cell, total we have N cells. We use the current input and the previous hidden state as the input to update the current hidden state. Here we use tangent H as a nonlinear activation function. We use this current hidden state as input to the output layer to produce the output. Here we use the softmax as the nonlinear activation function. For example, we use this matrix times vector H plus this bias, we generate a new vector. We use this new vector as an input to the softmax function to predict the normalize the probability distribution. Here we use defined as y with head. We use this prediction and his corresponding ground truth together, define the cross entropy, and then we define the cross entropy as a loss function at t+1 times step. So our goal is to calculate the gradients of the loss function error with respect to 5 model parameters, 3 matrices. First is WAA, WAA, and WAX, and 2 bias BY and BA. First, let's see how we calculate the gradient of the loss function error with respect to this WYA. Use the chain rule. First, we calculate the gradient of this error with respect to y with the head. And then now we calculate the gradient of y with the head respect to WAY here. Then now we need to backpropagate this gradient from a current state to the beginning. We don't care the future value. So here we just put all the result together. And then this for each time step, we put we add all the results over the total time steps. And then we get the total gradient of a loss function with respect to parameter W. For the same way, we calculate the gradient of a loss function error with respect to the bias BY. First, I calculate the gradient, and then we calculate this gradient. Then let's see how can we calculate the gradient of loss function with respect to this WAA. First, we calculate the gradient of error with respect to this y with head. And then same thing, we use the chain rule. We calculate the gradient of this y with head with respect to h t+1. Because this t+1, we have 2 contributions. One is from current W, one is from previous W in a previous cell through this previous hidden state. So we need to calculate them separately. And one is use this ht+1 directly calculate the derivative of this h with this WA. Secondly, we use through this ht, use the chain rule. And then now we put them together and then backpropagate this gradient from current state to the beginning. And then we add all the loss in the total time period, get a total gradient of the loss function with respect to WAA. And then follow the same idea. We calculate the gradient of loss function L with respect to this WX. Further calculate this gradient, because we have two contributions to this H T plus 1. One is WX in the current cell, one is in the previous cell through this previous hidden state. So we calculate them separately. One is directly derivative, one is through this new chain rule, calculate this distribution from the WX in the previous cell to this HT plus 1. And then we put them together. This T plus 1 is the first term, and the rest of them is second term. So we add all the loss over the time to get the total gradient of the loss function L with respect to parameters WAX. And finally, we use the same idea, calculate the gradient of loss function L with respect to bias BA. Same way we use the chain rule first, calculate this gradient, then calculate this gradient. Here we have two contributions. One is from current cell, one is from previous cell through this previous hidden state HT. We calculate them separately and put them together and calculate the sum over the time. We get the total gradient of loss function L with respect to bias BA. So once we get each of them, then we can put them together, get the total gradient. Then now we can use the gradient descent method to update the model parameters. For more details, please check with this reference. Thank you. Bye.